Hello, everyone. Right, okay, so let's start. This is the final webinar of this year, this academic year. So the next one is going to be in October, and you will be in year 13 by then. I hope, most of you. Right, so let me start. I have to say that I have done several webinars on this topic, and so yes, I've covered the topic quite extensively. I will be repeating myself, but I tried not to. Yeah, so I try to introduce something new in every year in this webinar. So let's start. So this is the topic of electrostatics. Now, the main two features that you need to understand about electrostatics is the electric field and the electric potential. Okay, so the electric field is probably easier to understand. The electric potential is slightly harder. And so I won't I'll briefly talk about these two. I won't derive them by I won't derive them, but yeah. So we start with the Coulomb's law. We start with the Coulomb's law, which is experimental. The Coulomb's law says that, by the way, I assume everyone can hear me well and see me well. Right, see my screen. Coulomb's law says that two charges Q1 and Q2 at distance r apart will push each other. There will be in this case, a repulsion force, and the force is equal by Newton's third law. If one pushes the other one pushes the first one with an equal force, and this force is equal to K multiplied by Q1, Q2 divided by R squared, where K is known as the Coulomb's constant. And you know, two charges, Coulomb really ripped off Newton's law of gravitation. You meant to say that the law of gravity ripped off the electrostatic law. What came first? The gravitational force of the... We don't know. We don't know which came first. Coulomb's constant. Although we will be writing it in a slightly different manner. We will be writing F is equal to 1 divided by 4 pi epsilon 0 Q1 Q2 divided by R squared. Okay, so epsilon 0 is known as permittivity of free space. Permittivity of free space. Now, it is a fundamental constant. And if I'm not mistaken, the speed of light is 1 divided by square root of epsilon 0 multiplied by mu 0, which is the magnetic permittivity of free space. So it is super fundamental. Formula for speed of light in vacuum. Yeah, speed of light is 1 divided by the magnetic permittivity of free space times the electric permittivity of free space. So like epsilon 0 is the fundamental constant, right? If you want to know, so it's a really important constant. You don't really see it in the school setting, but maybe you have. But these are identical. These are equivalent. It's just sometimes the Coulomb's constant can be expressed. Coulomb's constant can be expressed as 1 divided by 4 pi epsilon 0. Okay. So yeah, this is the Coulomb's force, Coulomb's law. You could think about it like this. So this is charge 1, and charge 1 produces an electric field around itself. This is an electric field. And let's say I take a random point at an electric field. And yeah, an electric field is a vector quantity. Electric field. It's the electric field. It is a vector. And it's defined as the force experienced per unit charge, Q0. Force per unit charge. If you think about it, the gravitational field, G, is the force per unit mass, right? Archie, thank you for that excellent question. What is a field? A field is a region in space where charged particles experience a force. Let me demonstrate. FET electric field. Okay. Oh, I really like this simulation. It's a simulation of fields, electric fields in this particular case. All right, so what do we have here? We have a positive charge here. It's a very small positive charge. We assume it doesn't really create a field around itself. If we place another charge, it produces a field. And you can see there's a field around this charge. What it means for this charge will be pushed by that field in the direction of the arrow. And the closer this black charge is to the red one, the greater the force, as you can see. Right? So a field is a region in space where charged particles experience a force. Does that make sense, Archie? Okay. Charged particle, charged particle experiences a force. And this is the field lines. And of course, if you release, if you place it like this and release, press start, the charge will fly away. And the task is to get it into the goal. So that's not a very difficult task, but it gets progressively more difficult, like this one. I'll just quickly demonstrate. So we'll need the trace, we'll need another field, and probably another one. Let's see if we can get it up. Need to get it to go slightly faster. Okay, even faster than that. Yes, I've done it. So, and then there's level 2 and there's level 3. So if you enjoy electric fields, you'll have a few pleasant minutes solving this, or maybe hours, maybe days. Anyways, give it a go. Hopefully not now. And the electric field is defined as the force per charge. Electric field is force per charge, and the gravitational field is force per mass. So yeah. Now, if there's a field and there's a point around that field, and this point is charge Q0, it's a small test charge, what we say it's a small test charge. And this test charge will experience a force. And we know that force will be 1 over 4 pi epsilon 0 multiplied by Q1, Q0 divided by r squared, where r is the distance from r. But the field is the force divided by Q0. It's the force per charge. So that's going to be Q1 divided by 4 pi epsilon 0 r squared. So the field from a point charge E is Q divided by 4 pi epsilon 0 r squared. That's important. Okay. Now, I need to briefly mention the potential of a field. Potential of a field. Potential of a field. So suppose you have a field, an electric field around a charge. And potential at point P, potential at point P is defined as the work done per unit charge to move a small positive charge from infinity to point P. Why would you need to do work to move a charge to point P. So let's say you have a small test charge Q0, which is very far from the field. Why would you need to do work to move it to this position? What are you working against? Exactly. You're moving it against the force from the field. This is a positive charge, so the field will be pushing against. So if you want to move, so it's in this simulation, that would be equivalent to moving the puck back towards the positive charge. So you actually need to do work. And the work divided by Q0 is defined as the electric potential. So VP, electric potential at point P. And you already know, you're familiar with the potential difference. So if you have another point Q, so the potential difference, so the voltage, so the potential difference between P and Q is equal to the potential at Q minus the potential at P. That's defined as the potential difference or voltage. Q0 is currently at infinity, so the field is infinitely small at this point. You are infinitely far away from Q1. All right, so you're infinitely far away, and as you move, the field gets stronger, stronger, and stronger. Well, it's easy to imagine. How do you move something at an infinite distance? Look, take a positive charge and a positive particle and start. It will go on forever. It will go on to infinity, right? And now imagine the reverse process. Does that make sense? Hope it does. And you see that this charge, the field is doing work on this charge, is doing work moving the charge away, and you need to do the same amount of work pushing it back to that position. So that's the potential of the field. And it turns out that the potential of a field is Q1 divided by 4 pi epsilon 0 r, which is very similar. The expression is very similar. So the field of a point charge, and this is a vector, but the potential of a field is from a point charge, is V equals Q1 divided by 4 pi epsilon 0 r. But this is a scalar. And I will demonstrate the difference to you. There's something called as the principle of superposition. It's a last thing I want to. Principle of superposition. Principle of superposition. So let's say we have 3 charges, Q1, Q2, and Q3, and all of them produce a field. And let's say you are standing at point P. So Q1 produces a field in this direction, and let's call it E1. Q2 produces a field in that direction, E2. And Q3 produces a field in this direction, E3. and it's a vector. The total field at point P is the vector sum of fields, if individual fields. And that means that the electric field at point P is equal to electric field 1 plus electric field 2 plus electric field 3. That's called the principle of superposition. So we superimpose the fields. So there are 3 fields and they produce a total field. Now, it's very important that the potential at point P is equal to the potential produced by charge 1 plus the potential produced by charge 2 plus the potential produced by charge 3. Potential produced, it's a really good expression, potential produced. Potential due to the field Q, V1, due to the field 2 and due to the field 3. And this is not a vector sum. This is an algebraic sum. So this is a vector sum, and this is an algebraic sum. Now, what difference does it make? Why am I so talking so much about this? Well, let's have a look at problem 1. 2 equal positive charges are placed a distance d apart. Okay, so we have a positive charge Q and another positive charge Q. And we are in the midpoint, so we are right here. So at this point, this field, this charge produces a field E1. And E1 is equal to Q divided by 4 pi epsilon naught. And now this is, if the whole distance is d, this is going to be d over 2 squared. All right, does that make sense? Yeah, any questions? Please let me know. The other charge also produces a field, but in this direction, because it's a positive charge produces a field in this direction, E2. And E2 is also equal to Q at 4 pi epsilon 0 d over 2 squared. But the fields are in opposite direction. And that means that the field, the total field, is 0. So the total field in the midway between 2 positive charges is 0. Let's have a look. Does it actually compute? Let's say we have a positive charge here and a positive charge here. And we can see that the total charge is, the total field is 0. One, because we have field this way, field this way. So it will not move up or down, okay, when I release. So it is in equilibrium. But let's talk about the potential. The potential V1 is equal to Q divided by 4 pi epsilon naught d over 2. And V2 is equal to Q over 4 pi epsilon naught d over 2. Now here, it doesn't matter. The direction does not matter. It's still positive. It's a scalar. And that means that the total potential is going to be 2Q divided by 4 pi epsilon naught d over 2. And it's definitively not 0. It is positive. It's a positive potential. What does a positive potential mean? Well, positive potential means that you need to do work to move a charge to that point in the field. But also that means if you place a charge in that field and release it, the field will do positive work. Even though the field is 0 at this point, overall, the field will make positive work. So the field will make this charge move. Let's see what actually happens when I start. It actually launches it with a velocity. So the work done is equal to the kinetic and final kinetic energy of the particle. So even though the field is 0 at this point, the moment it moves slightly off, it will go in that direction. And what I did is I tried to draw this. So I've placed two charges. I've placed one charge at point at x equals 1. I've placed one charge here, and I've placed another charge here at B. And I've drawn I've plotted the resulting field, the resulting potential. And this is how it looks like. Okay, maybe 3. Slightly simpler. So you can see that where the charges are, the potential is really large. But what we've done, we've placed the puck right here at the bottom of this valley. If you place a ball down here, where will it roll? It will roll along this line. So it's exactly what we've seen with the puck. If you place a puck right here, it will roll in this direction along the y-axis. Let's see that again. So these are the two peaks. We are right in between. We're not going up or down because the forces are balanced, but we are going sideways. So the gravitation, the potential of a field is like the height above the ground, if you think about it. In an electric circuit, a battery raises the potential, that it lifts the electrons to a higher potential, and then they can roll down, spinning a motor, or they can light up a light bulb on the way down because they can do work on the way down. Or if you remember the analogy of the electric of the water circuits and the electric circuits. Okay, does it make sense? Oh yeah, it can lie, but it's an unstable equilibrium. That's what we call an unstable equilibrium. It's very small perturbation and it will roll off. It's impossible to, well, it's almost, well, actually it is impossible to place it right in the middle because that will violate Heisenberg's uncertainty principle. Anyways, these are the charges and this is the field. The height is the potential. The height of this surface above the ground is the potential of that field, if that makes sense. Okay. Now, even though that at this particular point, the field is 0, but the potential is not. And if you release the particle, it will gain energy from the field. Caden, I'd love to, but I really want to do some electrostatics today. The uncertainty principle. Look it up. Heisenberg's uncertainty principle. You either know how fast you're moving or where you are, but you cannot know both at the same time. Problem 2. Imagine a copper ball of radius 10 centimeters and all free electrons are removed. So you know copper is full of free electrons. And imagine we managed to remove all of them. What would the charge be? I forgot the question. What is the charge? What is the charge on the ball? Okay. So you have a sphere, copper sphere, and the charge of one electron is 1.6 times 10 to the minus 19 coulombs. Assume one free electron per atom. So we need to know how many atoms there are. Okay. So well, we need the total mass. Total mass. Mass is volume, density times volume. So that is 8,900. I'm converting to kilograms per cubic meters. No, we don't need to take into account the charge of the nucleus because we are removing a single electron per atom. That means that every atom will be +1. So we have copper, and we are removing an electron, so it becomes copper plus. Right. We're not removing an electron from copper because copper is already ionized because it's an ion lattice. So it's already an ion. It's just we removed the free electron. Times 4/3 pi, the volume is 4/3 pi r cubed. So it's 8,900 times 4/3 times pi times r cubed, which is 0.1 cubed. So this would be something 8,900 times 4 pi divided by 3 times 1 cubed. So that's 37.2 kilograms. So mass of one atom is 64 multiplied by U. So it's 64 times 1 U, 1 atomic mass unit. So in the periodic table, 1 U is 1.67 times 10 to the minus 27 kilograms, which is 64 times 1.67 times 10 to the 27 minus 27. So it's 1.07 times 10 to the minus 25 kilograms. So the number of atoms is the mass divided by mass of atom, mass of ball. And so that would be 37.2 divided by 1.07 times 10 to the minus 25 kilograms. And that gives us 37.2 divided by answer is 3.48 times 10 to the 26 atoms. And we know that the charge of one atom is 10 to the minus 19. So total charge is equal number of atoms times the elementary charge. And elementary charge, so that's this number times 1.6 times 10 to the minus 19. That's a big number. It's 5.56 times 10 to the 7 coulombs. That's a lot of charge, times 10 to the 7 coulombs. So yeah, 1 coulomb is a lot. 10 to the 7 coulombs is really, really a lot. So two such balls placed 1 kilometer apart. And so the force is going to be Q1, Q2 divided by 4 pi epsilon 0 r squared. So there's going to be 5.56 times 10 to the 7 squared divided by 4 multiplied by pi multiplied by epsilon 0. Epsilon 0 is 8.85. Oh, my memory. Constant. Epsilon 0. A very handy calculator. If you manage to get one, the Casio 991. It's a very useful one because it has all the scientific constants on the back. So I need to choose constant number 32, which is epsilon 0. It's 8.85, yes. 8.85, I should have trusted myself, times 10 to the minus 12, multiplied by r squared, which is 1,000 meters squared. Okay, and if you do that, 5.56 times 10 to the 7 squared divided by 4 pi multiplied by answer multiplied by 1,000 squared. And that gives us, wow, that's ridiculous, 2.7 times 10 to the 19 newtons. Imagine two 10-centimeter copper balls, right? Placed 1 kilometer apart. And they would be attracted, or they will repel with a force of 2.7 times 10 to the 19 newtons. I wonder what's the force between the Earth and the Moon. Force between Earth and Moon. It's 1.9. What? It's 2 times 10 to the 20 newtons. Okay. What was between the Earth and the Moon? What was between Earth and Moon? Is 2 times 10 to the 20th in newtons. So it's only 10 times smaller than the force between. It's only 10 times smaller than the force between the planet Earth and the Moon. It's like, yeah, just increase. Make the radius 30 centimeters and 30. Not 30, no. Make the radius 20 centimeters and it will match the force. Not even 20. 10 centimeters more? So 15 centimeters, roughly. I'm lost in calculations. Too many squares and cubes, but yeah, it's a massive force. So bottom line is the electrostatic force is incredibly strong. So this is the conclusion that you need to bring. The conclusion. The electrostatic force. Static force is very strong. Okay, not as strong as the nuclear force, but it's a very strong force. So if you take a proton and an electron in the hydrogen atom, and you compare the gravitational force between them and the electrostatic force between them, the electrostatic force is 10 to the power 42 times bigger, which is massive. And it's 42, which is a magic number. Okay, problem 3. It's a Millikan experiment. Millikan was the first one to deduce the charge of an electron. Yeah, I actually measured the charge of an electron. So what he did, he had 2 plates. A positive plate, I'm simplifying, and a negative plate. And as you know from GCSE, that there's a field between them. There's an electrostatic field between them. Now you take a droplet of oil, that carries a negative charge. So it carries a charge of 2 electrons. So the charge, yeah. Now there are 2 forces acting on this droplet. First of all, there's the gravitational force, that's the mg. And on the other hand, there is the upwards electrostatic force. Okay. Then they have to match. So Millikan used a microscope to look at the oil droplets, and he changed the voltage between the plates. And so he changed the voltage between the plates by applying, and he noted when the oil droplet was suspended. And this way he worked out that the force, the charge can be a whole. What he deduced that the charge on droplet is quantized. What does that mean? Well, that means it could only be E, 2E, 3E, 4E, etc. And he worked out that E is the charge of 1 electron. So he worked out that there is a smallest possible charge, and you cannot have it doesn't split. Right. So the charge is a downwards force of gravity, which is mg, and that's equal to mass. Mass is density times volume times g. And the upwards force, the electric force, which is charge multiplied by the electric field. You will also learn in the assignment that if you take the distance between the plates is d, and the voltage between them is V, then the electric field, uniform electric field, is equal to the voltage divided by the distance. So the electric field is Q V over D. And then you just make them equal to each other, because the forces must be balanced if the oil is suspended in midair. So Q V over D is equal to rho Vg. And he worked out that Q is rho Vg divided by D divided by V. by volume. And the volume of a droplet is 4 pi, so it's rho v. Okay, that's volume, and that's voltage. That's unfortunate. Let's call it U. The electric field is U divided by D. QU. U. Rho V G D divided by U. So rho multiplied by 4/3 pi r cubed G D divided by U. Okay, so rho is from here. Is the charge of 2 electrons, right? So he worked out that there's 2 electrons. So the charge of 1 electron is rho 4/3 pi r cubed GD divided by U multiplied by 2. So density of oil is 800 multiplied by 4/3 pi r cubed. It's 1 micrometer. So it's 10 to the minus 6 meters cubed. Multiplied by, this is kilograms per cubic meter. Multiplied by G, so 10 newtons per kilogram. Multiplied by the distance. The distance is between the plates 8 millimeters. Multiplied by 0.008 meters. 2 multiplied by 820 volts. Okay, cubic meters cancel, kilograms cancel. So newtons meters. All right, so we have 800 times 4 divided by 3 times pi multiplied by 10 to the power minus 6 cubed, so it's minus 18 multiplied by 10 multiplied by 0.008 divided by 2 times 820. So it's 1.63 times 10 to the minus 19. Now the units is Newton meters divided by volts. That's Newton is kilogram meter squared divided by second squared. And the volt, well, volt is joule per coulomb. So that is kilogram meter, or sorry, Newton is kilogram meter per second squared, kilogram meter squared per second squared per coulomb. I'm going to leave coulombs because they're nice. So that is one. So Newton multiplied by meter divided by volt. That is kilogram meter divided by second squared. Volt is joule. So kilogram meter squared, second squared, coulomb. And meter squared cancels, kilogram cancels, second squared cancels, and we're left with coulomb. So Newton meter divided by volt is a coulomb. It's 1.63 times 10 to the minus 19 coulombs. And that's the elementary charge. Well, so that's how the experiment was done. Right? I mean, I was too busy doing the calculation, but that's the thing. So he put an oil droplet, and by measuring the voltage and measuring the distance between the plates, and by measuring what else did he measure? the density of oil, of course, and the size of the oil droplet, he was able to work out the charge of an electron, which we just did with you. Okay? So it's a very significant calculation. That's what I'm trying to say. It's a very significant. It was a very significant breakthrough in physics. A charge was indivisible at a certain point. The charge of an electron is indivisible. You can't have a charge of half an electron. It doesn't exist. Okay, so charge was quantized. Problem 4. We have 5 charges placed in the corners of a square. We need to find the force on the central charge. Okay, so the charges are all the same. They're 20 nanocoulombs. This square is 20 centimeters. Find the force on the central charge. Well, there are 4 forces. First of all, there's a repulsion force. So let's label 1, 2, 3, 4. Charge 1 pushes the charge in this direction. Charge 2 pushes the charge in this direction. That's F1, F2. Charge 3 pulls the charge because there's attraction. So F3 pulls this way, and F4 pulls this way. And this is easy to demonstrate. If we take a positive charge here, a positive charge here, they both push, and these pull. Okay. And it actually returns. Oh, that's very nice. Now I want to know what happens next. Anyways, yeah, that's the idea. And we just need to calculate one force because they are all equal. F1 is equal to F2 is equal to F3 equals to F4. That's equal to, we need to, the distance between this charge. Let's call it D. And this is A. So this is A over 2. A over 2, and this is A over 2. So we use Pythagoras theorem. So D is equal to square root of A over 2 squared plus A over 2 squared. So that's A squared over 4 plus A squared over 4. That's A squared 2A squared over 4, which is square root of 2 over 2A. So force is equal to Q times Q0 divided by 4 pi epsilon 0 multiplied by D squared, square root of 2 over 2A squared. Okay, so that is Q, well, it's Q squared because they are the same charge. So 4 pi epsilon 0, 2 over 4, so 2A squared. Okay, so this total force, so F1 plus F3, we can add them because they are, is going to be 4Q squared over 4 pi epsilon 0 A squared. and the same as F2 plus F4. I can these two forces add up, and now we can use well, Pythagoras. So we have two forces. So we have a force like this, and we have a force like this. We can add the two, and the resultant force, the total, F total is equal to F plus F squared plus F squared, which is square root of 2F, which is 4 square root of 2Q squared divided by 4 pi epsilon 0 A squared. And now we can work that out. So it's 4 square root of 2 multiplied by Q, which is 20 times 10 to the minus 9 coulombs squared, 20 nanocoulombs, divided by 4 pi epsilon 0 multiplied by A squared, which is 0.2, 20 centimeters squared. I hope I've done everything correct. So 4 square root of 2 multiplied by 20 times 10 to the minus 9 squared. 4 pi divided by constant 32 multiplied by 0.2 squared. So it's 5.1 times 10 to the minus 4 newtons. That's the total force. That's how you do it. You just find one force and then add them together. Now, the very, very new thing for you in the assignment would be the Gauss's law. Gauss's law talks about flux, electric field flux. So flux is how much of the field passes through a surface, if that makes sense. So imagine you have a surface and an electric field, and some of this electric field passes through that surface. So flux is how much field or how many lines. It's not correct to say how many lines, but you can think of it how many lines, or you can think of it as water. Thinking of flux. How much water passes through the surface, the frame? How much water passes through the frame? So similar to how much field passes through a surface. That's why it's called flux, right? Flux, like water flux. It's an influx of water. So, yeah, do you think you understand it on an intuitive level? Some feedback? We don't use curl and div here. This is it's just a more complicated calculus operators, which Meister effect. I can't say on the top of my head. I don't. Well, superconductivity is definitely related to this, but this is to do with magnetic fields. Oh no, so yeah, I mean, of course, Gauss's law is applicable for superconductors, but the idea of flux is just flux is how much. So imagine you can have a gravitational field flux. You take this best mouse mat ever, and if you place it like this, how much gravitational field passes through this mat, right? So this will be flux. How many field lines, right? So how many field lines can I capture with this? If I put it like this, I will capture 0 fields because the gravitational fields miss the surface, right? So in this position, the flux would be 0. And in this position, the flux would be maximum because it is perpendicular to the field. So the flux is defined as the electric field multiplied by the area exposed to the electric field. The bigger the area, the more field you can catch. So flux is the field multiplied by the area. And of course, if the angle is not 90 degrees, if they're not perpendicular, then you use an angle theta, EA cos theta. Or simply put, it's E times A, where A is a vector. Bizarrely, area of a surface is a vector. Well, it can be drawn as a vector if we define it as a vector of length of magnitude equal to the area, and the direction is perpendicular to the surface. And this way we can define phi, the flux, as the dot product of the vector E and a vector A. So here's the vector E, and here's vector A, dA. It's a small area, dA. So if you take the whole surface, it's an integral of E times dA. Okay. Right. So this is okay. Vector. So let's say you have a surface, and the area of that surface is A. A is the area. You can define vector A as a vector of, well, let's say it's 2 square meters. Vector of length of magnitude 2, and direction normal to the surface. So it would be a vector A. And modulus A is equal to the area, which is 2 square meters in this particular case. Does that make sense? Okay. Right, so let's look at this. This is example 5 from the assignment. I calculated the flux of the constant electric field through each side of a cube whose edges are parallel to the coordinate axis, and the length of each edge is 1 meter. Okay, so Apologies. So the cube has 6 surfaces. Looking at this surface, for example, we want to know how much electric field passes through this surface. Well, we can find a vector. What would be the vector of this area? A1, let's call it A1. What's the magnitude of this vector? 1, yeah. And the direction is perpendicular to the surface. So it's along the y-axis, right? So it's going to be 0, 1, 0. Now we take into this cube to be positive. In is positive and out as negative. Just a simple one. Into the cube is positive, out is negative. So this is A1. This is A2. The back surface A2 is symmetrical. It's going to be 0, minus 1, 0, because now it's going backwards. Sorry. What am I saying? Sorry, that's nonsense. We take the normal vector pointing, because it's a flat surface. The flat surface has 2 directions, either that way or that way, pointing into the cube. All right, so A2 this way is 0, minus 1, 0. Okay, this surface, let's call this one A3, and this is A4. A3 is going to be along the x-axis, so it's going to be 1, 0, 0, and A4 is going to be minus 1, 0, 0. And then finally, we have the top surface and the bottom surface. We'll call the bottom surface A5 and the top surface A6. So A5 is 0, 0, 1, and A6 is 0, 0, minus 1. And yeah, so the flux is F1 plus F2, phi2 plus phi3 plus phi4 plus phi5 plus phi6, and which is equal to this scalar product of E times A. So, and E is 1, 2, 3. So it's 1, 2, 3 multiplied by 0, 1, 0 plus 1, 2, 3 multiplied by 0 minus 1, 0 plus 1, 2, 3 multiplied by 0, by 3 is 1, 0, 0, 1, 0, 0 plus 1, 2, 3, it's minus 1, 0, 0 plus, well, you got the gist, 3, 0, 0, 1 and plus 1, 2, 3, 0, 0, minus 1. So this is 1, 2, 3, so that's going to be 2. That's voltmeters. Is it voltmeters? Yeah, volt times meters. This is minus 2 voltmeters, phi 2, plus 1 voltmeter minus 1 voltmeter, and this is plus 3 voltmeters and minus 3 voltmeters. And you can see that the total flux is 0. So the total flux through the cube is 0 because some of it going in and some of it going out. Okay, sure, Rahul. I was glad to have everyone here. Okay, so you have the flux going through the red surface is, what was it, 2 voltmeters. 2 voltmeters is the flux going through that surface. And minus 2 is going through the back surface. Well, of course, because the amount of going in through the front is equal to the amount of going through the back because it's a uniform field. Okay. Hope that makes sense. And finally, the final question. Find the flux through a sphere of radius r from a point charge placed at the center of that sphere. So we have a point charge, Q, and we have a sphere placed around the point charge. We need the flux going through that sphere. The electric field is in all directions, right? But because the way the electric field at distance is equal to Q divided by 4 pi epsilon 0 r squared, right? That's the electric field from a point charge. Electric field from a point charge. Now, for any surface that you take here, A, or a small, let's call it dA, for a small surface, dA, the flux is going to be E multiplied by dA. But E is the same. Well, it's a vector, but it's the same magnitude. It's the same at any point on the surface. So if I want to find the total flux, this is d phi, total flux phi total is going to be equal E multiplied by the area of the sphere. So phi total is going to be the E, so that's Q divided by 4 pi epsilon naught r squared multiplied by the area of a sphere, and area of a sphere is 4 pi r squared. Which is equal to Q over epsilon naught. And this is Gauss's law. This is known as the Gauss's law. The flux through a closed surface surrounding a charge, Gauss's law, flux through a closed surface surrounding is equal to Q over epsilon naught, where Q is the charge enclosed by the surface. What does that mean? if you take a surface, any surface, and you place a charge inside, the total flux through the walls of this surface, or through the imaginary walls of this surface, they don't have to be real walls, the total flux is Q divided by epsilon naught, which is really, really important. Would that be minus 4 pi r squared since going away from the surface? Well, yeah, you can say it's minus, but it's going out. Yes. I chose to ignore signs, but it's a matter of choice. It's not a strict law that you don't have to choose in positive and out negative. It's not like that. So I wouldn't use minus here. Gauss's law is without a minus. It's the total flux penetrating the surface. And if the sphere was 2 times larger, well, nothing would really change because the flux, suppose the sphere, suppose sphere is 2r. So that means that the electric field would be weaker, 4 pi epsilon naught 2r squared. But the area is now 4 pi 2r squared. And the flux is EA, which is Q over 4 pi epsilon naught 2r squared. I don't even need to simplify. Multiply 4 pi 2r squared, and it still cancels and becomes Q over epsilon naught. There's no difference. The shape and the size of the surface does not matter. And this is the key point of Gauss's law. And I'll finish here. I'd love to have a rest. And we'll be very busy preparing for the next year of COMPOS. So those of you who've completed 75% of the assignments, not 75% of each assignment, have 75% of assignments to a decent standard. Decent standard usually means 50% completion, but it's not a strict, right? So I didn't know about this in year 12. We won't, unfortunately, we won't accept anyone new in year 13. They can join the follow along program. They can join the follow along program, and but I don't think we have any places for new year 13s. Yeah, but they're welcome to join the webinars and go through the assignments by themselves. Yeah. Yeah, you enroll automatically. You will receive an email, but if you want, if you can fill in the application form on the website. It makes life easier for us. I think we will ask you all to complete application forms at some point, but if you go to our website and fill in the application form, that won't hurt, right? So just that we definitely know that you're interested in carrying on, so we don't have to chase you. You will get an email. You will get an email saying that you have completed COMPOS, and it will be a PDF, and it will be like your certificate of completion. It's not a certificate, it's a letter. It's a letter of completion. So you will receive that in a few months once we get all the data in, and it's yeah, it takes a long time to process all this data. Till when you have access to your current assignments? I haven't thought about this. Well, probably until September. Yeah, we're not for the form. Deadline for the form would probably be mid-September. All right. So everyone who has fulfilled the requirements to progress to the next year, you will receive an email asking you to probably fill in an application form. Yeah. Right, I have a quick question about inequalities. If final answer contains values that would cause the denominator to be 0, we need to show that we reject those values. Well, you just don't include them in the answer. Like, you can't, like, for example, if you have an inequality x multiplied by x plus 2 divided by x plus 2 less than 0, of course you divide that and it becomes x less than 0, but your solution cannot be from minus infinity to 0. No, it has to be, you have to exclude the minus 2. So it becomes from minus infinity to 2 and from 2 to 0. You don't need to say out loud that you exclude it, but you can't include it in the answer, if that makes sense. Sorry to send the same message twice. You might not have seen it, but assignments for the file corruption have not yet been marked. No, if you submit them, you can still submit your work. If you are missing a few assignments, you can still submit your work, as long as it's there, as long as it's decent quality, decent standard. We will be looking through over the summer, and yeah, that's fine. Even if it's not marked, don't worry about it. We will be looking at it at some point. So as long as it's there and the work is done, you have a place for year 13. Deadline to submit all assignments. We will let you know, but we'll probably give you an extra month to finish it. So mid-August, roughly. Do you need to submit your assignment separately again? I'm not sure. I don't understand what that means. If you're missing some assignments from that you haven't completed, you can complete them. We'll give you some more time to finish them. You need to do 75% of the assignment. So you've been given 20 papers, 10 on physics, 10 on maths. You need to complete 15 in order. So as long as you submitted 15 assignments in total throughout the year, and they are of decent standard, you get a place to. When I say decent standard, it's just like you've done them, right? You have not submitted an empty paper for some reason, or yeah. Let's say, well, no more than 3 standard deviations from your mean. We will let you know. Okay. Okay, that's it. That's it for the webinars this year, and hope you enjoyed the flight. And I'll see you back next year. welcome.